All right, thank you very much, Ben. So my aim now is, let's see how far I make it. I want to spend the first, let's say, a little less than half of this lecture talking about a completely different way in which strong convergence has allowed us to access different applications and kind of a different viewpoint than on the story. And then I will say very briefly some words about different methods that people have used to prove strong convergence. And then I will try to say some things about strong convergence itself, some actual nice properties of strong convergence. Let's see how far we get. So I want to talk about a story, a completely different story, which we call intrinsic freeness. So in order to discuss this, let me go back to the very first paper of Hagerup and Torbjornsen. So let's talk about what they proved. So now we're in the world of Gaussian random matrices. Well, we've left the world of groups, okay? So now we're in the world of Gaussian random matrices. So pick R independent GUE matrices. GUE matrices are just, they're complex self-adjoint Gaussian random matrices whose distribution is invariant under conjugation by any unitary. That's what the U stands for in GUE. So these are the most nice, most symmetric Gaussian random matrices that you can imagine. Okay? And there is a limiting object. So as always, I'm going to call this tuple Gn. And there is a limiting object called the free semicircular family, which is the most beautiful, most natural, non-commutative object that you can think of. It's one of the most basic ideas in Voiculescu's theory. These are just the free analogs of the Gaussian, right? I'm not going to define it. You may look it up. And what Hagerup and Torbjornsen proved, so I want to write it. Of course, Hagerup and Torbjornsen, I can just say the words. Hagerup and Torbjornsen proved that G of n converges to S strongly. Okay, that's their theory. We don't need to really say anything else. I want to present this in a kind of different way. So let me define, just like we did in the case of the random lifts. Let's look not at general polynomials, but let's look at linear polynomials with matrix coefficients. Okay? So let's pick some d by d self-adjoint random matrices. Not random, sorry, deterministic. I just pick some d by d random matrices. These are n by n. Okay. Let's pick some just fixed d by d self-adjoint random deterministic matrices. And now we can define a random matrix which looks like this. It should go from 0. It's A0 tensor d identity plus some I is 1 to R of AI tensor d identity. Right, so this is really a linear polynomial of the GUEs, but with arbitrary matrix coefficients. And of course, if we believe this story of Hagerup and Torbjornsen, which we do because it's correct, then the natural limiting object should be the same thing, where we just switch out the GUEs with these free semicircular variables. Now, the main theorem of Hagerup and Torbjornsen is that if we look at these are self-adjoint operators, right? So they have a spectrum as a subset of the real line. Then the Hausdorff distance between the spectrum of these n-dimensional matrices and the spectrum of this limiting object. So just to use a notation that we use very often in these papers, we call it X free, that's the free object. Converges to 0 as n goes to infinity. Right? So we fixed these d by d matrices. They don't change as you change n. We let n go to infinity, and then basically in the limit, this random matrices converge to this deterministic matrix. And in this case, you even get almost true. Very good. So now, this is kind of a special instance right? These are linear polynomials with matrix coefficients. In general, one might be interested in nonlinear polynomials. One of the kind of extremely influential and major insights of this paper of Hagum Torbjornsson is that this statement actually implies strong convergence. So that's called linearization. And in order to prove strong convergence, so convergence of every polynomial, it's actually enough to prove convergence of the spectra of linear polynomials, but you have to allow arbitrary matrix coefficients. Now that's a fact. I mean, it's a basic fact about strong convergence, that they use. So really, their main random matrix result is about these objects. But for the purposes of what I want to explain to you right now, actually, I care more about these objects anyway. Okay, so it was more convenient for me to phrase it like this. Good. So this is a wonderful result. But if you come from operator algebras and you want to understand these objects, right? So if your interest is in X-free, then this theorem shows you that there's a way of constructing these X-frees out of matrices, right? And that gives you very strong implications about the operator algebras that live over here, generated by these SIs. Right? However, if you're coming from somewhere else, for example, from applied mathematics, you may be much more interested in these guys, but these random matrices are kind of very special, right? They're D by D block matrices. You can think of this as a D by D block matrix where each block has IID entries, roughly speaking, right? And these are kind of contrived objects. They don't show up in the wild, right? They're designed objects. Right? So from the point of view of applications, the most interesting case is the case n equals 1. Okay? So the case n equals 1, let me just give it a name. I just call it x rather than xn. So let's just to spell it out. The random matrix X is just a matrix where these are 1 by 1 GUE matrices. That means they're just scalar Gaussian random variables. So this is just a matrix, deterministic matrix, plus some I is 1 to R, AI, GI, where GI are independent, real standard Gaussian random variables. So why is this the most interesting case? It's because any D by D random matrix with jointly Gaussian entries is of this form. Because any jointly Gaussian vector can be written as a mean vector plus some matrix applied to a vector of independence Gaussians, right? And all I've written here is this is a completely general matrix whose entries are linear function of some vector of independent Gaussians. I can generate any Gaussian, as long as I choose R sufficiently large, right? So I may have to choose R as large as D squared. But every Gaussian random matrix is of this form. I'm sorry, self-adjoint, thank you. I heard something in my ear, but I didn't know what it was. Self-adjoint. There. I'm making these matrices self-adjoint so that the spectrum is real. The matrices are not self-adjoint. There's an easy construction if you're interested in the singular values. The complex eigenvalues are a different matter. Was there a question?
Is that a complex Gaussian then?
Real Gaussians. Because it's a self-adjoint matrix, so a self-adjoint 1 by 1 matrix had better be real, right? Yes, right. So these are real Gaussians. But these matrices can be complex. Did I write it? Yes. These matrices can be complex as long as they're self-adjoint. Are we good? Now the question is, what does this have to do with that, right? So maybe I want to just emphasize the kind of, what's the intuition behind, why should we ever expect such a thing to be true, right? Now there's an intuition, it doesn't actually come, at this level of generality, it doesn't come from Howard Torbjornsson, it just goes back to the original results of Voiculescu, right? So these semicircular variables are free, right? Now, they're algebraically free. They're actually stronger. They're freely independent. But we're talking here about norms. So let's just for reasons of intuition, let's just think of these as being algebraically free, right? So every word in these objects is distinct, right? There's no relations between these S's. Right? But that's not true for matrices, right? Matrices can never be algebraically free. So why should we expect that if I take a sequence of random matrices that they become free in the limit, right? Well, by construction, these matrices, their law is invariant under conjugation by any unitary, right? That's what this GUE property says, right? So their eigenspaces are uniform random, right? Each of these matrices has completely independent, uniformly random eigenspace. Now that means these matrices, they must be extremely non-commutative, right? Because each of them has a completely different set of eigenspaces. If the matrices were to commute, they would all have to have the same eigenspaces, right? Because you can simultaneously diagonalize them. So if you take each of the matrices has a uniformly random eigenspace, they have to be extremely non-commutative. And the larger you take the dimension of these matrices, the more kind of incoherent become the eigenspaces of different matrices, and so the more the non-commutative they become. And in the end, in the limit, they are so non-commutative that they behave completely freely of each other. Right? That's the intuition. It's the notion of asymptotic freeness. I mean, it's a vague statement, but it's a picture that you should have in mind. Right? On the other hand, if we take n equals 1, then each of these matrices is a 1-by-1 matrix. And 1-by-1 matrices are highly commutative, right? So the entire intuition goes out the window, right? So there's really no reason to expect that, right? I mean, the fact that these things behave freely as n goes to infinity, you may expect it. Then, of course, what exactly does it mean free, right? Free doesn't just mean algebraically free. It's a specific objects that are over here, but you may expect that you get some kind of freeness in the limit. But if you have 1-by-1 matrices, they commute. They're very non-free. So it seems like there should be absolutely no reason why this statement, right, or this model, x free, should say anything whatsoever about this random matrix. Right? So the rather surprising thing is that it turns out that not to be true. So there turns out to be a very large class of situations where we can understand completely general matrices like this. So arbitrary Gaussian random matrices. We can't understand every Gaussian random matrix, but you'll see in a moment when I write it down. I can start from just a completely general Gaussian random matrix. And it turns out that under some mild assumptions, these matrices already behave like x-free, right? So this is a statement as n goes to infinity, right? But it turns out that in many cases, like this distance is already small when n equals 1. And of course, this asymptotic freeness does not explain this phenomenon. It's a kind of different incarnation of where freeness comes from. It doesn't come from the same place that you would expect it to come from. So let me write down a theorem, and I'll just say, I mean, I don't have a lot of time, so I won't say much about, I don't say much of anything, but I'll say a little bit about where it comes from. But the theorem that I'm writing down is, it's from 2 papers. So I'm going to give some bound, just like in Hausdorff, this is a qualitative result, but I'm going to give some quantitative bound on the Hausdorff distance between the spectra, not of xn and x3, but of x1 and x3. The result is actually better than what I'm writing. I just want to simplify it a little bit for presentation purposes. So we take the Hausdorff distance between the spectrum of x, that's x with the scalar Gaussian, greater than a constant. Then there is some parameter which I'll explain in a moment. And then there is something logarithmic in the dimension, plus t, bounded by e to the minus t squared for all t. So this c is a universal constant. And this parameter v tilde of x, okay, I'll write it, but I don't think you will see anything from what I write, but I will just give some examples to illustrate it. It's some parameter that depends on the covariance structure of x. So first we can look at the expectation of x minus the expectation of x squared. And the second object here is the norm. What is this thing? So x is a d by d matrix. So it has d squared entries, right? So this is just a d squared dimensional Gaussian vector. If I just think of the entries of the matrix as a d squared dimensional Gaussian vector, it has a d squared by d squared covariance matrix. That's cov of x. And I just took its operator. And then there is the powers to make it homogeneous. Is it good? Now, you can't really tell much from this parameter if you've never computed it. Okay? But it turns out that in many examples that we care about, this parameter is very small. And as soon as this parameter is small, this statement is saying that x, the spectrum of x, is close to the spectrum of x3, right? So for example, you guys can't see when I write there, right? So if x is a d by d, let's say GUE or GOE, or really anything like that, one of these standard matrices, right? Just the d by d matrix of IID Gaussian entries, then this v tilde of x is of order 1 over d to the 1/4. Yes?
If you replace the v tilde by the matrix alignment parameter, is this statement still true?
If I replace it by what?
The one that Trop invented, that matrix alignment parameter that I forgot.
Yeah, the alignment of some tensors.
No, we don't know if it's true. Maybe, but we don't know. But you're asking something I haven't defined, so we don't know. We don't know that. Okay, let's stick to this parameter for now. Okay, so. What's the point here, right? So we switched from n to d. So I reserved n for the dimension of these matrices I tensored on, but here n equals 1, right? So we're really talking here about the d by d matrix. And I'm saying that if this is a d by d GUE matrix, then this parameter is 1 over d to the 1/4, which goes to 0 very quickly as d goes to infinity, right? So this result says that the Hausdorff distance between x and x3, if in the case of a GUE, in the case of a GUE, the spectrum of x3 is the same as the semicircle distribution, right? And it says that the Hausdorff distance goes to 0 at a rate at least 1 over d to the 1.
It's a normalized GOE, yeah.
Yeah, I always use
Spectrums
normalized.
on
Right. Yes. I didn't say it, but I've normalized them so that their norm is of order 1. On the other hand, if I take x to be a band matrix, this is just an example. So I take a matrix that's 0 outside a band of width W, and in the band it just has IID Gaussian entries, and the correct normalization here is 1 over square root W. This will make the norm be of order 1. Right? So for this matrix, v tilde of x is of order 1 over the bandwidth to the 1. Yes?
Sorry, I don't understand the definition of v tilde. Is that the variance of x as a matrix?
What is the variance of x of a matrix? It is what it is, what I wrote here. You take x minus the expectation of x squared as a matrix. I take the expectation of that random matrix, that's a deterministic matrix. It just depends on the covariance of the entries of x, right? I take the norm of that matrix, right? But forget about what is written here. If you've never computed these kind of parameters before, you will not see what this is about, right? So you just have to, that's why I'm giving an example. But we actually have, the result is more precise, and there are many other parameters that appear, which are even smaller than this guy, okay? So I just want to give you some bulk. The point is there's some parameter which, when we compute it on examples, turns out to be small, right? So in particular, you notice, right, if we want this to go to 0, right, we want that to go to 0, this had better go to 0. But we only have a log here, right? So as soon as W is much larger than some polynomial of log D, right? This entire quantity over here goes to 0, and we have that the Hausdorff distance of the spectrum goes to 0. Does that make sense? And we can do the same thing if rather than taking x to be a band matrix, we can take, let's say, H1D, or H1 to HR to be IID band matrices, right? And we can take X to be some I, AI, tensor, HI, where HI, AI are some deterministic matrices. And the same parameter will be polylog D. Right? And if you now apply that result and you use the linearization trick, right, that I talked about before, what this result will show is that actually if I pick independent random band matrices with bandwidth W, as soon as the width of the band increases polylogarithmically in the dimension, you already have strong convergence. But in a sense, that shouldn't be allowed, right? Because these band matrices, this whole intuition that the eigenspaces are random is completely false for these band matrices. Now, these band matrices have localized eigenvectors. The eigenvectors are localized in space, right? So it completely breaks, in some sense, the intuition about that freeness is being caused by, I mean, you know, one can argue about it, but this is just one example of a completely general phenomenon. Yes?
Is there a negative result in this direction, saying that for some W that's also polylog, you break strong convergence?
If W is smaller than log D, you will break strong convergence. That's very easy to see, actually. It's even for a single matrix. Because as soon as W is smaller than log D, right, then even the largest entry of the matrix will already be larger than the free limit. So the power of the log is not optimal, but other than that, it's the best you could hope for at this level of generality. I'm just giving some examples. You know, you can pick any kind of pattern here and have a similar stuff.
But in this case, the limit is not semicircular, right? It's more complicated, and it's not free either. So somehow this thing that you're saying with the fact that the eigenspaces are not in general positions is reflected in that limit.
No. In this case, the limit is semicircular. Oh, it is. At least if you take, okay, I mean, I'd have to check, but if you take it to be circulant rather than that.
Circulant it is, but otherwise.
In the limit as W goes to infinity? Okay, I have to think about this.
If it goes as a constant fraction of the width, then it's.
Okay. But I can engineer this to be semicircular to be. So in a sense, you see, I mean, the point here is that you see the freeness, in asymptotic freeness theorem, the freeness comes from replacing these guys by matrices which behave freely. Here these things are scalars, they don't behave freely at all. Somehow the freeness comes from the structure of these coefficients. Right? Now this is why we call this intrinsic freeness. This is freeness that's not caused by the object you stick into it. Right? The random matrices that behave freely this freeness of this object is not caused by building this up out of elements which are free. It's caused because the structure of these matrices is causing the behavior of this matrix to be indistinguishable from a free object. And that's why we call this phenomenon intrinsic freeness. So I am really like skipping over the history, and I'm not going to say anything about how this is proved. But we were inspired in this by two papers. One of them was the paper of Hagrup Torbjornsen, and the other one was a paper of Joel, who had this idea that one could have some kind of non-commutativity coming from the structure of the AIs, and he introduced some parameter, which I haven't written, which March was talking about, that is supposed to capture this non-commutativity. And somehow, if you put together these two ideas in the right way, with the right tools, you are able to show that this is a kind of quantitative strong convergence statement that applies to all kinds of random matrices that maybe you would not have expected to have any relation with strong convergence. So the nice thing about this thing is that, if we're studying operator algebras or we're studying spectral gaps, right, we're allowed to design, right? We are looking, for example, for optimal spectral gap. We have a universal lower bound, and we are allowed to design the nicest possible objects that we can that meet the gap, right? On the other hand, if you're an applied mathematician, okay, then your life is intrinsically dirty, okay? So pure mathematics is beautiful, applied mathematics is inherently dirty, and you deal with all sorts of nasty stuff that comes up in applications. And you don't have the luxury of saying, this is not regular enough for me, I'm going to replace it by something that's uniform at random, right? So you're faced naturally with all kinds of crazy matrices that come up in practice, right? And you have to deal with them. And when you have some tool like this, it shows that even though these matrices don't seem to have any business of behaving nicely, actually in many situations this parameter turns out to be small. And as soon as that's the case, this theorem allows you to compute exactly where are the edges of the spectrum. We have other theorems like this that talk about the spectral distribution of the eigenvalue. So it's not just about the edges. But the edges, I think, is the most powerful and the most difficult result in this direction. And so this has a huge number of applications. And for example, in this paper, you can find some series of applications in applied mathematics. You just kind of hit them with this. And then the nice thing is that this X-free is beautiful because now we're in the world of free probability. And that means that we can actually compute the spectrum of X-free. And we can reason about it. Right? So this allows you to understand, to leading order exactly how these very general kind of random matrices behave in terms of free probability. Was there a question? Yes. I don't remember. I think the first one was called matrix concentration inequalities of free probability, and this one is called matrix concentration inequalities of free probability 2. I hope that helps you.
But the first paper did not say 1.
It didn't say 1. Yeah, I don't know how people do this. By the time I write, I never know that there's going to be part 2 when I write part 1. So sometimes people have, I don't know. Yes, they clearly have a better plan than I do. Yes.
So if you change Gaussians by other, so Gaussians are very important or not?
No, but we have a paper with Tatiana. Tatiana, are you going to talk about it? Okay, Tatiana is going to tell you about it. We can replace these models by much more general non-Gaussian models. But but what I want to say about it is that we don't do that. It's in some sense completely unrelated to the story. Because the way we do that is we have very general theorems that say that we have a very large class of non-Gaussian models that behave like Gaussian models. So we have a kind of analog of this theorem where this is a non-Gaussian random matrix, but this is not a free object. This is just a Gaussian random matrix. And then there's some other parameters that show up here. Right? And if you combine that with this theorem, then of course you can compare the Gaussian with the free, and then you get a comparison with the free. But in a sense, extending to the non-Gaussian case, at least in the situations where we can do this, which are quite general, that in itself has nothing to do with freeness. So that's a separate story. But it's very useful, of course, to be able to do this for non-Gaussian matrices. Are there any more questions? Yes?
How does intrinsic freeness behave with finite rank perturbations?
What is a finite rank perturbation? Just tensoring on a finite dimensional matrix?
Yeah, or even like adding one to say the H's in this example. Like a bound of the rank or something.
I mean, if you just tensor, like I did over here, I just tensored on some finite dimensional matrices, it's perfectly fine. It doesn't add anything. Just, something depending on, yeah, we can check it, but it doesn't make any difference. Just the max of the norms of the AI, that's something.
I was going to change the H's.
To what?
Add some deterministic, add a rank 1 projection or something.
Oh, well, that's just a typo. I'm allowed to have any mean. Yes. And you see the comparison, I erased it, but the X3 also had an A0 tensor identity in it. So the mean doesn't make any difference. Yeah. Sorry, yeah, I just forgot to add it, but you can have here this tensor identity. Does that answer the question? Yeah.
So you're actually able to recover the BBP phenomenon, right?
BBP, yeah. We can recover many things. We can prove BBP phenomena in non-homogeneous situations, which, I mean, would be, we have quantitative versions of them. And, so, I mean, on the other hand, all of these beautiful strong convergence results that I talked about in the first lecture, they're completely out of reach of this kind of theory because we have these logs. Right? So depending on the application, this log D may be completely uninteresting, or it could be important, right? So it depends. So these are kind of orthogonal directions. But I just want to give a flavor. I think of this as a kind of different incarnation of the strong convergence phenomenon that applies in a completely different set of random. Are we good? Okay. That's all I want to say about this for now. It's just a story. Okay, now I want to just spend 5 minutes talking about proofs, right? And again, I'm really going to say almost nothing about it because we're going to hear lots of talks about this. Okay? So I think I can't do justice to this in the same way as the other talks. Okay? So I just want to say some general things. First of all, from the very beginning, the problem of proving strong convergence has created beautiful interactions between operator algebras, which is where this comes from, and random matrix theory. And from the very beginning, it required the introduction of new machinery. So for example, this linearization argument in the original paper of Hagerup Bjornson was had a huge impact on subsequent developments. And they needed it in order to prove the strong convergence. Another example is what Benoit talked about yesterday. Bordenave and Collins, they developed a kind of theory of operator value non-backtracking, which is really a kind of non-trivial tool that one can use to handle these questions. But okay, I'm giving the talk, so I'm entitled to tell you my favorite methods. And I think, my favorite methods there are two different methods, but they somehow apply in very different ways the same idea, which is, let me call it recent methods are based on some kind of interpolation. And what I mean by this is that, it's actually quite different than classical random matrix theory. So people who come from classical random matrix theory, from mathematical physics, how do they reason about random matrices? You write down some spectral statistics. Let's say they expect a trace of some polynomial of a random matrix or some moments of a random matrix. Then either you can compute, either you have kind of explicit formulas, you can sit down, you compute, you take the limit, you get what you get in the limit, right? Or what often happens is that you write down some kind of equations that are satisfied approximately by the spectral statistics, and you realize that when you take the limit, these equations become closed form equations. And as mathematical physicists call these self-consistent equations. And then you solve these equations, okay? So these are kind of classical tools of random matrix theory. And in these classical tools of random matrix theory, you don't take seriously the notion that there's a limiting object for these random matrices. It just, you take spectral statistics and you compute the limits. But what is the limiting object, right? But the asymptotic freeness, the idea of asymptotic freeness is giving us some operator that's playing the role of the limiting object, right? And once you have that idea, you can also realize that maybe that gives us a philosophy for how to prove random matrix things. Maybe we shouldn't try to compute what happens and see that in the limit it behaves like a limiting object. Maybe we should just take this literally and try to somehow deform the finite random matrix to the infinite limiting objects and try to bound how much error you make along the way, right? And this is somehow the idea behind these interpolation methods. And in many ways, they turn out to be more powerful than what came before because they give very powerful quantitative results. So I think it doesn't tell you how to do it, but I think the philosophy coming from asymptotic freeness and from operator algebra is also giving us inspiration for how to reason about these kind of random matrix problems. So there's really two completely different ideas here. One of them is that you could literally, I'm putting it between quotes because that's not actually exactly what happens, but let's say we want to compute some spectral statistic, right? So the expected trace of some, let's say, polynomial of xn, right? Say we want to, or x, whatever. Let's say we want to bound this in terms of x free, whatever it is, right? So what we could try to do is we just kind of try to interpolate just create some kind of interpolation, right? When t equals 1, this is x. When t equals 0, this is x free. So we just made some kind of continuous deformation from x to x free, right? And now if I want to show that x and x free behave the same way, then I can just take ddt of this, right? And show that it's better than small, right? That's a kind of general philosophy. Now, I put this between quotes because this is kind of meaningless the way I wrote it, because you see, this X is an n by n matrix, this X free is some infinite dimensional object, they don't even live on the same space, so what does this mean? And how exactly you implement this, that's of course that's important. Okay? But this kind of technique was kind of independently introduced. The first one is by Collins, Yone, Taro. And Felix will talk about it, I think, on Friday. Yes? Yeah. A bit, right? And by March, and Afonso. Myself. So technically speaking, not technically speaking, this paper came before that paper, but we were ignorant and we didn't know about it. So, what Benoit and Alice and Felix did is they used this to give a quantitative version of the Hallgrupp to Bjornson result. And Felix has later extended this very beautifully in many directions. And we use this exactly to prove this theorem, or at least one direction of this theorem. Okay? And then the difficulty here is, okay, you take DDT and you try to compute, and you have to understand why that should be small, and that's where all of the interesting stuff happens. Okay? But it turns out to be a very powerful result, or a very powerful approach that gives us a quantitative. The other method, which is kind of maybe more surprising, is let's do the same thing. Let's take some polynomial, let's say, of, now I take xn, right? I index it by dimension n. So in many cases, it turns out that we can, for example, if you have random permutation matrices, right? And like in Bordenave-Collins, this is nice enough, you can compute this, and it turns out to be some nice function. Okay. It turns out to be a rational function, right? So it turns out to be a nice function. And you see, what are we interested in? We want to show that this converges to whatever it is in the limit as n goes to infinity. So we just want to bound the difference of this function at 1 over n and then this function at 0. Right? That's another kind of interpolation, but the parameter is different. Here the parameter, we introduce the parameter t that interpolates between the matrix and its limiting objects. Here we chose as our parameter t just 1 over the dimension. Right? So that parameter was already given to us. But if this is a nice function, then you can do what seems like to be an idiotic idea, which you can just Taylor expand this function. Well, I mean, you know, this is bounded by the L infinity norm of the derivative of f, phi times 1 over n, right? So if you can bound the derivative of this function, then you're done. It seems dumb, but the amazing thing is it works. And, but it's, Jorge and Anthony will tell you a lot about it on Friday. So this was introduced by Anthony, Jorge, Joel, and myself. And of course, I'm sweeping under the rug all the interesting parts of this story. But it turns out that this gives us ridiculously easy proofs of many of these hard theorems that we had before. And this technique also gives us, it allows one to prove, for example, the story about high-dimensional representations, which would have been very difficult to do using previous. So you're going to hear about both of these methods on Friday. There are going to be a series of 3 talks in the morning, right? Which are going to tell you everything that you want to know about it. The challenge to whoever's speaking.
Perhaps worth noting that if you want to prove strong convergence, you need a second-order Taylor expansion, yeah?
Yes, so I'm highly oversimplifying here. So I need to leave something for Friday.
So, still not obvious.
I have how much time? Like 10 minutes, 15? Yeah. Okay. So having said absolutely nothing about actual mathematics, right? So in complete opposite of Ben's talks, I thought I would spend the last 10 minutes telling you some secrets. Not big secrets, very small secrets, which will be obvious to half the audience if you've ever seen an operator algebra. But so rather than telling you about how to actually prove strong convergence, I want to tell you some basic properties of the strong convergence property. And the reason I want to spell this out, even though these are somehow well-known things, is that some of these ideas, if you know them, they're very simple, and we use them very heavily inside proofs of strong convergence or to improve strong convergence results. Some of them I've never actually seen written down. I should say I learned many of these things from Michael de la Salle. So, there seems to be some kind of folklore knowledge about how you manipulate strong convergence that, so I thought I would kind of spell out some basic facts and try to just give a hint about why they're very useful. Okay, that's good. So Right? So some of them are going to be more basic than others. Very good. So the first one is about scalar versus matrix versus operator coefficients. Okay. So I already alluded to it. So strong convergence says that the norm of Pxn converges to the norm of P of x, right? And the question is for what P, right? So initially we said this is true for all P. This, by definition of strong convergence, we have this for all P, which is non-commutative polynomials with complex coefficients, right? So scalar polynomials and their adjuncts. Right? So what are these, right? What are these objects, right? So this is P is sum, let's say, over I1 to IK. Let's say sum over K is 0 to Q. And we have some coefficients, I1 to IK, of x I1 to xik. Right? So it's a non-commutative polynomial. Right? Does it make sense? And now the question is, okay, so these are scalar coefficients, but can we replace these by other things? For example, could we replace these by matrices? Or could we replace these by operators? Right? And you already saw that in the applications, I naturally needed these to be matrices. Right? It was very important in the applications because that gave me that gave me an ability to encode these models that I showed you for optimal spectrograms. Right? So there's a basic fact, right, that strong convergence for all scalar polynomials implies strong convergence for all scalar polynomials with matrix coefficients. So if you can prove this for scalar polynomials, then you automatically can prove this if I replace these scalar polynomials just by arbitrary deterministic matrices, tensor the product. And this is really an easy fact if you know how to do it. I'll just give a hint. So say I take a polynomial P with matrix d by d matrix coefficients. I can just view this as a d by d matrix of polynomials with scalar coefficients, right? So it has entries, right? So if P is here, right, then P is just some d by d matrix where each entry of the matrix is a polynomial in scalar coefficients, right? Now, it's obvious that if I take the norm of P, it will be lower bounded by the norm of any of the entries. Because to go from this to that, I just have a projection, right? So a projection lowers the norm, right? Right? To go from a matrix to an entry, it's just a projection. On the other hand, it's upper bounded, obviously, by d squared times the maximum of the entry. That's just by the triangle inequality. Right? I write this matrix as a sum of a matrix which only has a one non-zero entry, right? For each of the entries, just apply the triangle inequality, I will get that. Right? So what this shows is that if I know strong convergence for these scalar polynomials, then I get strong convergence for these matrix-valued polynomials up to a factor of d squared, right? A constant factor of d squared. That's not true the same as having it up to a constant factor 1, right? However, norms have the beautiful property that if I take the norm, let's say the norm of P star P to the K is the same as the norm of P to the 2K. Now this is just a polynomial here of degree 2K. If this was a polynomial of degree D, then this guy is a polynomial of degree 2K times D. Right? So it's again a polynomial. Does that make sense? So if I now apply this thing not to P, but to that polynomial, right? Then I get that this polynomial converges strongly up to a factor not d squared, but d squared to the 1 over 2k, which is d to the 1 over k. And then if I let k go to infinity, I get 1. So that's the proof. That's called the tensor power trick. It's a completely standard argument in operator algebras. But, you know, for example, if you're coming from random matrix theory, maybe it's not immediately obvious. So we can pass to matrices. Now, what happens if I pass to operators? So suppose I have a polynomial with operator coefficients. So this is some C-star algebra. So what if I wanted to do something with operator coefficients? That's something that would arise naturally, for example, for hyperbolic surfaces, though what I'm going to say here is not needed. So it turns out it's not always true, okay? It's not always true that strong convergence implies strong convergence with arbitrary operator coefficients. Now I just write some keywords. It's still true if A is exact. So exact is, I don't have time to explain, but exactness is a property of C-star algebras, or really of operator spaces. And if A is an exact C-star algebra, then if I have strong convergence for scalar coefficients, I actually have strong convergence for polynomials with any coefficients in an exact C-star algebra. And many of the algebras that we work with are exact. Right? So for example, all of the C-star algebras you have seen in my talk are exact. So the C-star algebra generated by a free semicircular system, the C-star algebra generated by the regular representation of the free group, these are all exact C-star algebras. So we could take polynomials, we could take coefficients which are themselves, let's say, polynomials of these objects, and we would still have strong convergence. Why is this useful? Right? If you remember in Ben's talk, he wanted to prove strong convergence of some random matrices tensor the identity, and some identity tensor some other random matrix. Right? So we have a model where we have these two random matrices. That's kind of annoying. What we could do is we could just pretend that these VNs are not random. Let's just replace these VNs by arbitrary matrices. Now we have a question about strong convergence of a single random matrix, UN, but with matrix coefficients whose dimension goes to infinity. That's a non-trivial problem, but that's exactly what is solved by all of these methods. So if I just condition on these VNs, if I can solve that problem, right, then I know that the norm of a polynomial of UN tensor identity tensor Vn goes to what? Or it's of the same order as the norm of a polynomial of, let's say, the limiting object, U tensor identity. But here I still have random matrices. And now after that, I want to use strong convergence of these guys to say that this guy can also be replaced by U. But now I've replaced these guys by operators. But fortunately, it's an exact C-star algebra, so everything works.
Could you remind us what an exact C-star algebra is?
No.
I don't know what it is.
The original definition of an exact C-star algebra says that there is a certain short exact sequence. As a non-operator algebraist, this means nothing to me. I mean, I know what a short exact sequence is, but not why that would be helpful. But basically, there's an equivalent operator space formulation of it, which says that an exact C-star algebra is the following. If you take any finite dimensional subspace, linear subspace of A, there is a completely positive or a completely positive map, or actually complete contraction into a finite matrix algebra. And what that means is that I can kind of uniformly approximate these norms by the same thing where I place these by finite dimensional matrices. And of course, as soon as I have that, then I just use strong convergence. Okay? So that's basically it. Yes?
Is there some sort of converse for this statement that you can upgrade strong convergence as long as A is exact? Something of the sort of like, if every time you have strong convergence and you take coefficients in A, and this strong convergence upgrades to the tensor, then A is exact.
Yes, and it goes exactly to the exactness story, right? Because the specific example with which you contend there is the quotient of the product of all matrix algebras by the direct sum, which captures exactly strong convergence. And so that sequence being exact is exactly what you want.
Okay.
Very good. I defer to the superior knowledge of our operator algebra colleagues. I gave you some example, but you see, we actually have, Jorge, I don't know if you're going to talk about this. We have methods, using these kind of methods, what we can now do is we can take quality, this gives us strong convergence, but not quantitative, right? This is a very non-quantitative picture over here. But we have a method by which we can take qualitative strong convergence and use it to prove quantitative strong convergence. If I know that something converges strongly without a rate, and you plug it into this machinery, you kind of get for free a very strong quantitative statement. Once we have that strong quantitative statement, we can use that quantitative statement to, again, build up more complicated models out of these simpler models. So for example, we prove strong convergence of graph products exactly like this. We can prove strong convergence of graph products by basically, we start with just one matrix. We apply this exactness argument to get some kind of Ben result. Then we use that soft thing to get a quantitative version. Then again, we use that together with some central limit theorem to build a more complicated model where you have interactions, and we can cycle like this. So you see, we really can leverage the C-star algebra structure of the limit in order to prove kind of random matrix results. And that kind of interplay is very fundamental to this, to this area of strong convergence. I've lost track of time, Ben. What is the? I'm out of time. Well, then I will stop here. Yeah.